1 minute after 1, so we're going to get started. Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Ben Hobbs and I'm going to be your host today. If you're just joining us live now, remember that you can ask questions anytime by clicking chat near the top left of your screen and typing in the questions in the pop-up window. Make sure you change the field to include attendees so that everyone can see your questions. And I'm going to be relaying these questions to our guests during the question and answer section of this webinar. So today our guest is Dr. Nathalie Ouellette. Nathalie is an education and outreach officer working at the Canadian Astroparticle Physics Research Institution at Queen's University. Thanks for joining us, Nathalie. I'll let you take it from here.
Great, thanks so much, Ben, and Stacy for helping to put this together. We actually changed our name recently to the McDonald Institute. We had a big launch event a few weeks ago. So it's not Spark anymore, it's the McDonald Institute, named after Arthur B. McDonald, who is a professor at Queen's and won the Nobel Prize for Physics in 2015. So today, what I'll be talking about, while I share my screen here, is all the different ways that you can do astronomy. A lot of the time when people think of astronomy, they think of someone using a telescope, maybe in their backyard. They're looking at something as if they were looking with a better version of their eye, essentially. But astronomy, there are lots of different types of astronomy you can do, and lots of different things in the universe that you can study depending on the tools that you use. So I will talk about all of the colors that we can see in the universe in what is very much a kaleidoscopic universe. So there's lots of different kinds of lights in the universe. We see in what we call optical or visible light, and really that's just an evolutionary quirk that we can see in that light, because our sun, which is really the most important thing in the solar system and assures that we can stay alive on the Earth, has its light at the brightest in the visible or optical wavelengths. If the sun was actually shining brightest in the X-ray, we would have X-ray vision, which would be completely different from what we can actually see. So stars can actually shine at a peak in the optical or the infrared or the ultraviolet. It's very rare for a star to shine outside of that range, but the star in our system, the sun, shines in the optical, so that's why we can see in the optical wavelength. You have wavelengths that go from the very, very energetic short wavelengths, very high energy, which we call gamma rays, and those tend to come out of radioactive reactions, radioactive decay, and they're actually quite dangerous for us. We don't want to be around gamma rays very much. Then as you go to less energetic wavelengths, we go into X-rays, which we know we use to look at our bones in our bodies, ultraviolet light, which we know the sun does shine, so we have to protect ourselves by putting sunscreen on. Then optical, infrared, which is what we tend to shine the brightest in. So if you've seen videos of people using infrared cameras, people are glowing at that wavelength, and animals too. Then you go to microwaves, which is exactly what it sounds like. It's what your microwave uses to heat up your food. And then you go to radio wavelengths, which is what we use a lot in our telecommunications. So we have all of these different wavelengths in the universe, and different things in the universe are shining all of these different wavelengths, but we can't all study them from Earth. And that is a bad thing for astronomy, but a good thing for humans to stay alive. So here you have a picture of how opaque or how much the atmosphere above us can block certain types of light. And to the left of the image, you see the very, very energetic energy, like gamma rays, X-rays, and to the right, you have the very long wavelengths, like radio waves. So you can see the very energetic ones. The atmosphere on Earth is very opaque to that. And that's really good, because if we didn't have the atmosphere blocking X-rays and gamma rays, we wouldn't be able to stay alive. We also have the very, very long radio wavelengths that are blocked, and some of the infrared in the center. So there's two main pockets where the atmosphere doesn't block out a lot of the wavelengths or the light that's emitted from the universe, and that's the optical, which is good because then we can use that light to see around us, and the radio, which is why we've ended up using radio wavelengths to do satellite communications, to have all of our television systems, to have all of our cellular network. So we use the fact that the atmosphere doesn't block radio waves to build our whole telecommunication system. But because we can only see those two types of wavelengths, we need to get really clever at to look at the other types of wavelengths that the atmosphere is blocking. So in order to do that, we need to use different kinds of eyes that are in different places relative to the atmosphere. So at the bottom there, you have radio wavelengths, which are the big dishes, the antennae, and you have optical wavelengths, and those can be on Earth because, as I mentioned, the atmosphere doesn't block those. We can also build things underground, like you have there the big sort of metal ball that's in Snow Lab, and that is actually looking at particles that are being emitted by objects in the universe instead of the light. Then you need to go up into space above the atmosphere if you want to look at the other wavelengths that are blocked by the atmosphere. So you have Spitzer on the left, which looks at infrared. You have Chandra, which is on top, that looks at X-ray. Galax on the right, which looks at the ultraviolet light. And you, of course, also have the International Space Station, which is in the center of the image. And that's because there's no substitute for having humans doing the experiments in space. So we've actually had at least one human continuously in space since the year 2000, since we've had the International Space Station up there. So we've been able to use our technology to plant instruments from 2 kilometers underground in Snow Lab to millions of kilometers above our atmosphere out in space to look at all the different kinds of lights that are being emitted by objects in the universe. Now, I mentioned that we can use telescopes on Earth to look at optical or visible wavelengths, but there's still an advantage to having really good space telescopes that look at those wavelengths out in space. The Hubble Space Telescope is a great example of that. It looks at optical or visible wavelengths, but it's in space, so it doesn't have to deal with things like light pollution. There's something that's really annoying for astronomers called atmospheric seeing, and all it is that the atmosphere is making stars twinkle. And it makes for a cute song, Twinkle, Twinkle, Little Star, but it actually makes for really bad images for astronomers. So if you can get above the atmosphere, you don't have that twinkling effect. So the space telescopes like Hubble don't need to deal with that. But it's very expensive to send up telescopes into space, and it's a lot harder to fix them if something goes wrong. So that's why it's good to have a balance between ground telescopes that are looking at the optical wavelengths and space telescopes that are more difficult and more expensive to manage, but can get really breathtaking images of objects out in space. Now, I'll talk a little bit about some of the different objects in the universe that emit at the brightest point at certain wavelengths. So we'll start at the very energetic in gamma rays. And I mentioned here on Earth, gamma rays are typically emitted by radioactive decay. So if you have like a nuclear reactor, you need to make sure that it's really well isolated because it's emitting gamma rays from its radioactive decay, which is harmful for humans. Out in space, some of the things that emit gamma rays are closer to us, solar flares. So I mentioned that the sun is very bright in the optical wavelengths, but sometimes you'll have a big explosion that happens on the surface of the Earth, on the surface of the sun, sorry, and that emits very strongly in the gamma ray. But luckily, as I mentioned, the atmosphere blocks that from us. In the video there, that is a sped up image. So the explosion actually happens over the course of many hours. It's sort of like a very slow motion explosion that happens. And the particles and energy and light that are emitted by the explosion sweep through the entire solar system. But we are protected by our atmosphere and our magnetic field as well. Gamma ray bursts are a very mysterious type of object that we're not actually sure exactly what they are, but we think they might be the collision of very strange and exotic stars called neutron stars. And when these neutron stars, who are very, very dense, collide together, we think they make the biggest explosions in the universe, actually. And when a gamma ray burst happens in a galaxy, that one point in the galaxy actually becomes brighter than the entire rest of the galaxy put together. So they're very, very bright, and we can see them very, very far out in space, but we just see a flash of light. So it's hard for us to tell exactly what is going on there. For X-rays, We can actually use X-rays to study something that we can't usually see because it's a black hole, and black holes tend to suck in light, or light cannot escape a black hole. But while a black hole is actively feeding, it can actually have the material falling into it being sped up so fast that it starts to emit in the X-ray. So if you see somewhere in the sky that is emitting in the X-ray, but you don't see any visible light there, there's a good chance that there's a black hole there that is actively eating material, and the material is emitting in the X-ray. So that's a good way to spot black holes, even though you can't see them themselves. You also have stars that are very massive that can die in a huge explosion called a supernova, and the supernova remnant, which is left over, can also emit strongly in the X-ray. In the ultraviolet and the visible light, like I mentioned, you have lots of stars that glow very strongly in those lights. But different types of stars emit in different parts of that range of light. Very, very hot stars tend to emit more in the ultraviolet light. So on the left here, you have an ultraviolet picture, and you can see a lot more of the specific dots, and those specific dots are very, very hot, young, massive stars. On the right, you have a visible picture of the exact same galaxy. It's using visible or optical wavelengths, and you're seeing a different population of the stars that tend to be a little bit more medium-sized, like our sun. Now, if you go to less energetic, even less energy, you have infrared light, which I mentioned we emit strongly in. So dust in the galaxies can also emit strongly in that wavelength, but planets can actually emit very strongly. So the Earth actually is radiating a lot of infrared light itself. And not just Earth, the other planets too. So on the right, you have a picture of the very top of Jupiter that was taken recently by a spacecraft called Juno. And that is emitting in the infrared. And you can actually see a bunch of cyclones or hurricanes that are swirling in the gas of Jupiter that are emitting in the infrared. One thing that's really good about infrared is that it doesn't, it's not blocked by dust inside of a galaxy or inside of a region with lots of stars. So this is an image of what's called a nebula. It's where stars are being born, and this is taken in the visible wavelengths. So it looks very dusty. It's very beautiful, but you can actually see a lot of the stars that are being born behind these curtains of dust. So we can look at the same area of the sky using infrared instead, and all of these new stars become visible now because infrared light can punch through that dust instead of being blocked by it like it is with optical or visible wavelengths. And finally, the radio waves that we see around us are actually very interesting because they're one of the proofs that a Big Bang happened. So we have something called the cosmic microwave background, and it's sort of like a background static all over the universe, and it looks exactly the same no matter where you look around you. And we think that's because the universe all started in one very, very small point where all of the characteristics could end up sort of normalizing or equalizing. Everything sort of looked the same, and then it puffed up really big all of a sudden. But that radio wave characteristic sort of stayed the same when it got stuck very far away from each other after the whole thing blew up. You can also have big jets that are being blown out of galaxies that emit in the radio waves. One thing that's very interesting about the cosmic microwave background, which is in the radio waves, is that if you have a television at home, many of you might not have one anymore because a lot of people just have a computer, but if you find a channel that is just like static or like white snow, the majority of that signal is actually the leftover of the Big Bang. That's your television that's able to catch the cosmic microwave background. So you're able to do astronomy in your home too, just by turning on a TV. So these are all of the different things that the universe is trying to tell us, and it's important for us to use different instruments located in different spots, because if we only use our eyes with instruments on Earth looking at the visible, we're only getting a very small portion of the story that the universe is trying to tell us. So that's why it's important to consider the entire kaleidoscopic universe when we're trying to study astronomy. And that's it.
Thank you so much, Nathalie. That was great. Just a quick reminder to anyone, if you'd like to ask a question, use the chat function, which is at the top left-hand of your screen. And make sure you change the field to include attendees so that everyone can see your question. I noticed we had one question come in from Dana Cam's class. She has a student that's wondering, and I know you already answered this in your presentation, but maybe if you could reiterate in case someone missed it. They asked, do any rays or wavelengths come out of black holes?
So they don't come directly out of black holes because black holes have a gravity field that is so strong, even light can't escape it. And that includes all of the different types of lights that I mentioned, from gamma rays all the way to radio waves. But as long as you're far enough away from the black hole, outside of a region called the event horizon, you can still have material that's interacting with the gravitational field of the black hole and can be sort of heated up, and that is light that you can see around the black hole. But inside the event horizon of the black hole, nothing can come out, unfortunately. So that portion of the black hole we still, and probably will never be able to look into.
Would you be able to explain spaghettification to us, Natalie?
Yes, spaghettification. So spaghettification is what would happen if you were to fall into a black hole. So, and this is if you're within the event horizon, you're inside the danger zone of the black hole at this point. So why spaghettification happens is pretty simple, but it's sort of counterintuitive because we don't have gravitational fields as strong as a black hole around us. So right now, if you're standing on the surface of the Earth, because your head is slightly farther away from the Earth than your feet, your head is actually feeling slightly less of a gravitational pull to the Earth than your feet. But because people are like 1.5 meters, maybe 2 meters tall, compared to the radius of the Earth, which is about 6,000 kilometers, I think, that's insignificant. It doesn't matter. But a black hole is very, very small, very tiny. So your height actually matters a lot more, and your feet are feeling a much stronger gravitational pull towards the black hole compared to your head. So your feet are going to fall down into the black hole faster than your head. So you're going to start getting stretched out like a noodle or a spaghetti until the molecular bonds that keep your body together can't hold on anymore, and you get snapped in half. And then each separate part of you that's just been snapped will be stretched out into spaghettis until they're snapped again. And if someone were to look at you being spaghettified from the outside of the black hole, because time is distorted by the gravitational field of a black hole, it would actually look to them like it is taking an eternity for you to get spaghettified. So it's a very long, very brutal way to die. So I would not advise falling into a black hole.
I don't think that sounds too good. We have a question here that asks, have we found any evidence of aliens?
So we haven't found any evidence of aliens, but we found a lot of interesting things like planets that have water or oxygen or properties that we think would be helpful to have life develop on them. One of the great things that happened a few years ago was when we had a spacecraft go near the moon, one of the moons of Saturn called Enceladus. Enceladus has these big sort of ice volcanoes that blow out smoke and ice into space. And we had a spacecraft pass through one of those ice volcanoes and look at what was being ejected out. And we actually found stuff in there that could have been food for life. So we see lots of things that are sort of helpful to life starting on these planets, but we've yet to find any evidence, direct evidence of life outside of Earth, unfortunately.
Could I just get you to stop sharing your screen, Natalie?
Sure.
Thank you. While we wait for some more questions to come in, I actually have a question for you. You mentioned that solar flares release large amounts of gamma rays. And we also have space-based telescopes. Would those solar flares interfere with those?
Yes, definitely. So we actually have some telescopes whose only job is to look at the sun, just because we want to monitor it all the time. And when there is a pretty big solar flare that happens, you'll see when the solar flare passes over the camera on the satellite or the spacecraft, a bunch of static starts showing up on the camera. And that's pretty, that's not a big deal, but sometimes you can have a solar flare completely destroy or knock out a spacecraft. And not only can it knock out a spacecraft, but it can actually knock out the electrical systems here on Earth. Our atmosphere and the magnetic field does a good job protecting us, but if a solar storm is super strong, it can actually get through a little bit. And that actually happened in 1987, where a lot of Quebec, New York, and Ontario had the entire electrical grid fried for, I think, a day and a half or something, like a little while, because there was a huge solar storm. So that's one of the important things about studying the sun, because it can actually mess with our technological systems a lot. So it would be helpful to be able to predict when a solar storm is coming.
Thank you. We have another question from Mrs. Cam's class, and they're asking, do we have any idea what a singularity is?
A singularity is what we call essentially the very center of a black hole. So a black hole is difficult to study because we can't shine light on it. We can't really take any data from it, because if we try to send anything in it to study it, not that we are close enough to a black hole to have done that yet, but even if we were, it would eat up the spacecraft. So we only know about black holes through sort of how it interacts with its surroundings and through math, essentially, so theoretical physics. And when we write out our equations, it seems like a black hole is infinitely small and so infinitely dense, which doesn't really seem to make much sense. So that is one type of singularity. That's a singularity that we would call a black hole. They might also mean the singularity in the sense that some people think that at some point humans will be able to create an artificial intelligence which will overtake us. And that is something that I'm less an expert on, and I'm hoping doesn't happen in my lifetime. But that is another type of singularity, at which point, I think machines would take over and then we would be in trouble.
That doesn't sound too good. We have a question from Notre Dame Catholic Secondary School, and they are wondering, how close are we to colonizing planets like Mars?
That's a great question, and it's something that is on a lot of astronomers' minds, because the next big missions in terms of sending people out into space is to go to Mars. We've done the moon in the 60s and 70s, and I think it ended in the 70s. Mars is the next sort of spot we want to hit. And NASA and lots of other private companies, even like SpaceX, they want to go on Mars within 10 years. NASA's a little bit more conservative. They're saying 2030. But that is sending someone to Mars. Colonizing Mars would mean making it a friendly enough environment for humans to start living there and building a society there and having children there. And then it would be like you would have Martian babies, essentially. That is significantly more far off. When we look at how slow some of the progress has been in terms of getting people to the moon or getting people back to the moon, it can be very hard because when you're dealing with human life, you don't want to take any risks. When you're sending out a spacecraft, it's very sad when they explode and they don't get to do any science, but at least no one died in the explosion. It's money that's been spent, unfortunately. But if we're starting to send people out, we have to be very, very careful. And we don't necessarily know how careful we're going to have to be in colonizing something like Mars. Mars will probably be the first stop, but I think that we're still several decades away from colonizing a planet.
Darn, I was hoping to be on Mars in a couple of years. We have another question coming in, and they are wondering if the rings around planets like Saturn have any effect on the environment of that planet.
So the rings are actually, the person who asked this may know this, but I thought it'd be good to mention just in case others don't. The rings aren't actually solid objects. We tend to see pictures of them and they just look like a few solid rings around the planet, but they're actually relatively tightly packed together dust and ice that are around the planets like Saturn. And you can often actually get moons that are embedded inside of those rings. So it's the effects that they can have on a planet to some degree can be similar to the effect of having a moon like our moon. around our planet. But because the planets that do have these rings, which are Saturn, Jupiter, Uranus, and I think Neptune has some very, very thin ones, they're so much more massive than Earth, and their rings are proportionally a lot smaller than the moon is to us. It doesn't have a huge effect, but it makes for some striking images.
Interesting. So we've got another question from Notre Dame Catholic School, and they're wondering, how good are movies like The Martian and Gravity and Interstellar at depicting survival in space conditions?
So the three that were mentioned are actually pretty good. If you go down and you start looking at lesser known science fiction, or you go to sort of like the, you know, B-list or Z-list types of science fictions, it starts getting pretty bad. But the good thing about those movies that were mentioned, they've actually hired scientists who consult on the science in the movie, and they say, well, this would happen like that. This wouldn't really happen like that. It's not completely accurate because, one, the situations that are depicted have never really happened before. So to some degree, we have to guess. And two, sometimes 100% accurate science doesn't make for the best storytelling. But for the most part, Hollywood is really making a huge effort to try and get the science right in those situations. I'd say that Gravity is something that could potentially happen, and it's called the Kessler effect, when you have a sort of cascading domino effect where one thing smashes and you get a bunch of like little parts, and then all of those parts smash into something else, etc. And it's something we're actually really worried about with all the space junk flying out there. Sandra Bullock was very lucky in that movie, but that could possibly happen. And I think for The Martian, I think that's pretty accurate because it's the one that's sort of closest by in the future in terms of what's possible. Interstellar is very far out there, so that's hard to say exactly how someone would survive on a planet in another system entirely after having been through a wormhole.
Very cool. So I've got one more question for you here. And I know you mentioned there was a particle detector that we kept miles underground on Earth. So what is the benefit of having a particle detector underground when there's so much getting between your detector and where the particle is coming from?
So the particles that are trying to be detected by these detectors, it's not just your everyday sort of run-of-the-mill particle. They're very, they're particles that don't tend to interact a lot with the material around us. So for the most part, there's two types of particles that are being studied in those underground labs: neutrinos and dark matter particles, hopefully, because we have no proof that a dark matter particle exists yet, but we're trying to study it. And the thing about those particles is that they could pass through kilometers and kilometers of material, and they would likely not interact with that rock or, you know, the side of a building. A neutrino, actually, you can make it pass through 1 light year of lead. So we're not even talking kilometers anymore, like a light year of lead. And it has a 50% chance of interacting with the lead. They really interact rarely. But luckily, in your thumbnail right now, about 50 billion neutrinos are passing through your thumbnail every single second. You don't feel them, they just don't interact. So these are very rare interactions we're trying to detect. And we have so many other particles buzzing around us because they're coming from space or because of radioactive decay around us. Those things can be blocked by the rock. And so if we're trying to detect very strange particles like neutrinos or dark matter above the Earth, it's like trying to listen to a tiny, tiny sound when you were like, you know, near a jet engine that's like blasting into your ears. If you can go down underground where the rock is blocking a lot of the cosmic ray particles from space or the radioactive decay, and you're careful in making it a very clean environment, you're taking away it's a factor of 50 million, essentially, that you're taking away from that background noise. It's still very hard to detect those particles, but you have at least a fighting chance to detect them because the noise background is a lot lower.
Interesting. So we've got time for this one last question. And the question is, if light gets close enough to an event horizon but does not enter the event horizon, would the light slingshot around the black hole?
So we think that if you've seen Interstellar, actually, we think that it would sort of be warped. It might even be, if there's a light ray, it might even be split into two, and you would sort of get this strange disk around the black hole that sort of traces the event horizon. So there is definitely a gravitational effect that you'll see. It's not really slingshot. It's more like it's warped. It's something that we call lensing. It's sort of like the gravitational field is acting like a physical glass lens with the light. So it will warp the light around the black hole.
Well, that's all the time we have for today. Thank you, Dr. Ouellette, for taking the time to talk to us today.
Thanks for having me.
No problem. So next week on PIR Live Events, we're going to be discussing vaccinations and their role in keeping children and adults protected from the spread of infectious diseases. More information about these webinars and other PIR educational programs are available at pirweb.org. Thank you for tuning in and have a wonderful day.